Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Okay, so time's got to rush, so we're going to start on time for once, or 5 minutes late. So it's a great pleasure to introduce Vlad. So Vlad is currently at Northwestern, and this is something slightly different because he's a real economist, and he's going to talk to us about simple procurement auctions. So,
thank you very much for having me, and thank you very much for coming to the talk. So, okay, I'm an economist incarnate, and I'm going to show you a couple of things about procurement auctions. So I'm going to show you results from a couple of papers. All of them are actually co-authored with one of my colleagues, Jeroen Swinkels. So in real life, first price auctions are of enormous practical importance because a whole bunch of firms are using them. The government is actually using them. Sometimes the government is even mandated to use them. But despite their prevalence, they have a couple of drawbacks from a theory perspective. And there's two downsides, essentially. They are, first of all, very hard to compute in terms of equilibrium. I mean, I can write you down the system of differential equations, but the solutions are, you don't get closed form solutions, first of all. Second of all, the solutions are going to depend on a whole order of belief things, which, let me put it this way, I'm doing this for a living, and I would have a hard time advising anybody how to bid in one of those auctions. Secondly, if the auction is asymmetric, it has also implementation problems. I mean, you would have a very, very hard time knowing exactly how to bid in one of these auctions, despite their simplicity.
So asymmetric?
Hmm? Oh, asymmetric meaning that your costs, I'm going to talk about procurements, are distributed differently than my costs. That's, let's keep it at this very, very simple level. Okay, so what I'm going to show you today.
You say that they're different bidders.
Different bidders, yeah.
Well, of course they don't. That's why they're different, right?
No, we're talking here about. Sure, absolutely, but the problem is from a, how should I put it, from a theory perspective, from a game theory perspective, it's we don't think of them as, you know, your realization of a cost is different than Peter's realization of a cost. That's perfectly fine, but they can come from completely different distributions. So you might have a more advantageous cost distribution than Peter. Right? As far as I know, as an auctioneer, I don't know where your cost is coming from. Right? So that's essentially the issue.
And first price just means the highest bidder wins.
Highest bidder wins and actually pays his price, pays his bid. In this case, since it's a procurement auction, it's the lowest bidder wins. You're selling a contract. Okay? So what I'm going to show you today are some very, very simple and intuitive ideas which we came up with to analyze these asymmetric first price auctions, and a whole bunch of advice on implementation. And so we started thinking about these auctions in a procurement setting. Again, there's a whole bunch of potential suppliers out there, and they each draw a cost from some distribution, and I'm trying to allocate the good, or the contract rather, as efficiently as possible. So even though everything I'm going to show you today is in a procurement setting, if you flip things around, you can think of it as standard auctions as well, in which you have a whole bunch of buyers and one seller. For simplicity, I'm going to start with a very, very simple case, which is almost intractable theoretically. You have two sellers, 1 and 2. Each one of them draws their costs independently from cumulative distribution, say F1 and F2. Might be a better cost distribution, might be a worse cost distribution. Some regularity assumptions on the distribution. We're going to assume that it has a log concave density and it's twice differentiable, twice continuously differentiable. For simplicity, just keep this notation in mind. We're going to restrict ourselves to the case without loss of generality that the cost distributions are actually based on a compact support 0, 1. Notation for the reverse cumulative. And here's the trick, which we're going to introduce. From a buyer's perspective now, you can have a preference. and a preference over the supplier. So I prefer Peter's product because he's a more reliable supplier, he has a better product. God knows, in terms of technology, he fits better than me. He fits better with me than anybody else in this room. So from the buyer's perspective now, when he purchases at a price P from supplier I, he gets a benefit of VI minus P. Here's the important thing, this delta. This delta is, if you want, the quality difference between suppliers in the mind of the buyer. Right? So we're going to say that supplier 1 is preferred by the buyer by an amount equal to delta. Right? So at every single price, I'm delta better off if I'm buying from supplier 1 than from supplier 2. Right? So that's the differentiation parameter. Which in yes, so for the purposes of this talk, assume this to be common knowledge. I have lots of things to say about when it's not common knowledge, but for the purposes of today, think of it as common knowledge. Yes, they're deterministic. Right. So it's not a bargaining problem, it's a simple auction problem. Okay? Remind me at the end if I have time to actually make some comments about the common knowledge aspect of it. Okay, so in this formulation, you can think of the auction as being isomorphic to a situation in which I'm shifting the cost distribution of player 1 by delta to the left. It has a better cost distribution. So whether I'm looking at the problem in this terms or in the isomorphic transformation, it's one and the same thing. Good. So
this is getting very much advanced. Then what we mean by that? Just can you slow down a little bit?
Sure.
We're not all experts on options.
I understand that. Okay, so you can think of this problem in two ways. Either you and Peter have some cost distribution and I prefer Peter by delta at the same price, or you have different cost distributions in which Peter's is better by, it's just shift the entire distribution by delta to the left. He has lower cost at every single possible realization. Okay?
This is because cost is around the variable.
Yeah. As far as the auctioneer is concerned, yes, cost is a random variable. If I would know Peter's cost, then the problem would be very simple. Right? I would just approach you and tell you, hey, I'm going to pay your cost. The problem with the auctions is that I don't know the cost.
So are you assuming the delta is a fixed constant, or can it be a function of D1?
No, I'm going to...
I prefer by 10% Peter irrespective of what the price is.
Perfect. I'm going to assume for the purposes of this talk, it's just a constant. Right? So the motivating example for this work came from a consulting case way back in which my co-author worked, in which Boeing was thinking about procuring engines for the aircraft. And they had figured out that, I don't know, GE engines are better than Rolls-Royce engines by $50 million. Now, if GE bids, if Rolls-Royce bids substantially less, then you might consider buying Rolls-Royce engines. Okay? But I'm going to show you one of the big extensions here. You can think of, in the most general version of the model, you can think also of proportional cost distributions. Okay? So,
What's the problem you're trying to solve? So if I'm myself or a supplier, I just say I'm having these auctions for engines. You bid. If you bid more than $50 million better, I'll buy you. Otherwise, I'll buy Complementary. Right? So he doesn't have a problem to solve. He just announces the auction and takes the highest bid.
the lowest bid, actually. So the problem is this. If you do that, I'm going to show you that's a suboptimal.
Oh, for the buyer?
For the buyer. For the buyer, it's horrendously suboptimal.
Oh, what else?
I'm going to show you in just a second. You can actually, not that. That's one extreme of the things you can do.
And these distributions, these F distributions, are these what so when the seller, the guy who's producing the engines, does he say, I don't quite know what they're going to cost me, it'll cost me $100 million plus or minus a bit because of uncertainty, or is this the buyers, the procurers?
It's the buyer.
Understanding.
Excellent. It's the buyer's belief about where these costs are coming from.
The buyers believes about his supplier's cost.
Exactly. We don't know them, right? I mean, the problem would be very simple. I mean, I wouldn't be standing here if you would know for certainty what the cost is. You would just approach the guy and say, I'm going to pay your cost, and that's it. Everybody would walk home happily. Problem is you don't know what his cost is, and he's not going to reveal his cost trivially to you. Well, delta has to do with the valuations of the buyer, right? I mean, how much I value, I don't know, GE's engine over Rolls-Royce's engine, right? Exactly, right? The costs are going to play crucially in the price, which is going to be generated in the auction. Is that fair? Okay, more questions on this? You can think of this as it has many different interpretations. It could be either quality, it could be reliability, it could be cost of doing business, cost of switching business from one guy to the other, whatever it is. P is going to be a price determined at the auction, right? I'm saying at any different price, right? If buyer I and buyer J offer you at the same price, you're better off by delta from buying from buyer 1 than buying from buyer 2. Okay? The price is yet to be determined. The price is going to be run in the auction. Good? Okay, so okay, here are a couple of things you can do with an auction. So common approaches to simple auctions in this universe, because the optimal auction is extremely complicated. I'm going to show you in just a second. So the most common approach is what's called request for proposals. Right, so what you have suggested is, okay, you submit a bid, the other guy submits a bid, and I'm going to pick the bid which, given my preferences, is the best for me. Okay. We're going to look at first price handicap auctions. I'm going to define them formally in just a second, which is the following thing. I'm going to define a handicap. Instead of $50 million, I'm going to say, for example, $30 million. And I'm going to say that as soon as my preferred player comes within 30 million of my unpreferred supplier, I'm going to buy from my preferred supplier. And that's announced. And also a second price bonus auction, in which the rules are, again, very simple. I'm going to announce a bonus which has the following implication. The two bidders are going to submit bids. I'm going to pick the lowest bid out there. And if my preferred guy happens to be the winner in that auction, I'm going to pay him a bonus equal to whatever it is, 30 million, 20 million, whatever I announce.
Who's your preferred guy? Is this the guy with the smallest delta?
With the highest delta, right? So make it player 1.
Say number 1.
Yeah. So if player 1 wins, okay, if player 1 has the lowest bid, I'm going to pay him on top of what I'm paying him due to the auction contract. I'm going to pay him a bonus, whatever it is, 25 million, 30 million, whatever I announce it to be. If the other guy wins, I'm not going to pay him anything. It's on top of the auction contract. Okay?
Did you announce that?
I announced that, right? I'm committing myself to these rules. So I'm going to essentially say, look, I'm going to favor player 1 by 25 million, by 30 million, by whatever it is. And you can have basically these two implementations. A first price implementation, in which the bid which you're submitting is the price which you're going to be paying, or your price which you're going to be receiving. And the second price implementation, which is the simple Vickery mechanism, which says, okay, if player 1 wins, then he's going to be rewarded based on player 2's bid. If player 2 wins, he's going to be rewarded based on player 1's bid. So,
Is that last thing another alternative? The thing you said about rewarding based on each other's bids. Is that any of these three?
yes, that's the second price bonus auction. So, a second price auction in general has the following characteristics. Okay? You make a bid, your opponent makes a bid. Okay? The guy with the lowest bid wins. It's a procurement auction. But he's being paid based on the other guy's bid. Okay? On top of that, we're going to tweak it by adding a bonus to it. All right? The first price implementation is the standard thing which everybody knows and most people use, and I'm going to show it's completely idiotic, actually, which is you're going to be paid based on your bid. All right. So, can we say anything systematic about the choice here? That's basically our problem. knowing, again, we cannot characterize the equilibria. We can write the differential equation, but we don't have closed order solutions for the equilibria. And fortunately enough, the answer is yes. And let me put it this way. State of the art, or kind of the gold standard literature of the literature in this field is a paper by Maskin and Riley from 10 years ago, which says the following thing. If you're indeed in one of these asymmetric universes, then a standard first price auction does better than a standard second price auction. Standard meaning no bonuses, no handicaps, no tricks. Just plain vanilla first price auction, that's better than plain vanilla second price auction. And this has been used by many people to justify the choice of a first price auction over a second price auction. And we're actually going to reverse this result in some sense. Okay, so the tool, I'm not going to insist on that too much, but I mean, for those of you who are interested, everything relies on row concavity. We're going to look at the curvature of these distributions in terms of their generalized concavity, called row concavity, and we're going to get good predictions based on that, or we're going to get important qualitative features of the allocation based on that. And along the way, we actually generalize one of the classic theorems in the field, Prekopa and Borel. But that's less important.
Sorry, is this about kind of in the optimum auction framework where we're trying to do best for the buyer?
Yes. So here, exactly. So we're very good. Maybe I should have mentioned that. So we're putting ourselves in a buyer's perspective. Right? What kind of mechanism should I design for my procurement? Okay, so if you're in Boeing's shoes, what kind of competition should you foster between GE and Rolls-Royce? Okay, what's the best for you? Okay, so
Is the difference between a procurement option and a regular option just kind of trivial version?
yeah, it's mutatis mutandi. Right? I mean, so you get results from one, you can just translate them into the other. It's much easier, sorry, 1 second, Peter. It's much easier to interpret it in terms of a procurement auction because I can say, look, I prefer Peter because he has a better product. In terms of a standard auction in which you have one seller and many buyers, it's a little bit less intuitive what it means I prefer one buyer. Maybe there's a minority contract going on or stuff like that, but it's less intuitive in that sense.
Yes, just I have heard of second price options in the case of a single buyer, multiple, single seller, multiple buyers. I guess in this case, if you had Rolls-Royce and Boeing and Rolls-Royce were offering their engines at a higher price and Boeing GE bid less,
Mm-hmm.
they would, the buyer would still commit to paying more, to paying what the figure that was.
Right. I'm still committing to buy from, for example, in a first price handicap auction, I'm still committing to buying from the guy with the higher bid,
Right.
simply because I have a preference towards him. Okay? If the bids come within, say, $20,000 or $20 million,
Right.
I'm going to buy from my preferred guy.
Sure, but imagine that there was zero. You didn't have any preference.
Then a symmetric auction is the optimum. Then basically no handicaps or anything. Then the problem is actually quite simple. The problem is the Myersonian problem solved from back in the 1980s, the symmetric auction in which you submit a bid, I submit a bid, and whether it's first price or second price.
Right, but if I were to do second price, the interesting thing is that as a buyer, I still commit, I look at both bids and I know that I'll pay the higher of the two bids.
Yes.
The question is, who do I pay to? I don't pay to get the highest actually, I pay to get the lowest.
Exactly.
I just have never thought about sort of second price auction in the case of procurement.
Sure. Or let me put it differently. Right? I mean, if second price is kind of too weird of a concept, think of it as a standard implementation, open auction. Right? So prices keep on falling. I'm announcing falling prices, and people signify whether they're in or not. At some point, the second lowest cost guy is going to drop out, and that's going to be the price. Okay, so when you think second price, think of open auctions. Maybe that's more intuitive. They're perfectly equivalent within this framework. Good. So, rules. Sorry, Peter, you had a question earlier.
No, just trying to explore what best means. Best just means maximising this difference in
No, best means two things. Right? I'm trying to maximize the surplus of the auctioneer, which means both price competition. Right? I can foster price competition very easily, as it was suggested. Right? I mean, I can just make you. I can always choose the lowest price guy, but that means I'm sometimes half the time I'm choosing the guy which I don't prefer. So what I'm trying to do is maximize my expected surplus. Right? So it's essentially achieving a balance between quality and price in one go. Good. So, definitions. So, the rules of the game. First price handicap auction with handicap A. So I'm committing myself to a handicap A, it's just a number, which says that if the bidder 1 wins, if and only if his bid is at most A above the bid of his opponent, right? So my preferred guy, I'm going to allocate a contract to him whenever he comes within A of the bid of the other guy. Otherwise, I'm going to give the contract to my non-preferred guy. The winner receives their bid. So the price which I need to pay for the contract is B1 if player 1 wins and B2 if player 2 wins. And each bidder is restricted to bid at most 1. Remember, I made the cost distributions without loss of generality. I'm considering them to be between 0 and 1. In other words, I'm not allowing anybody to bid above their maximum possible cost. That's a very, very simple restriction that says simply, hey, I could just come to you and say, I'm paying you the highest possible cost you might possibly have, and I want to deal with you. So I'm going to rule that out. Now, there exists an equilibrium in pure increasing strategies for this game. But again, the problem is a computational one. We don't know what it is. Good. What we're going to be interested in is the allocation induced. Meaning, given the equilibrium, in the space of possible costs which the two competitors might have, when am I giving it to Mr. 1? When am I giving it to Mr. 2? So the allocation is going to be defined by this phi function, which has the following thing. If my cost as a preferred guy is below phi applied to the transformation C2, then that's the case where player 1 wins. Conversely, that's the case when C1 is greater than phi of C2, that's when player 2 wins. The geometry. I'm sorry? These are the equilibrium bid functions. Equilibrium bid functions.
What is an equilibrium bid function? You mentioned equilibrium several times. You haven't told us what equilibrium you're thinking of.
Oh, it's the standard Bayes-Nash equilibrium for the game. The standard Bayes-Nash equilibrium for the game.
Okay, what's a Bayes-Nash equilibrium?
Okay, a Bayes-Nash equilibrium is going to be a function beta for you, a bid function beta for you from your possible costs into bids, and a function for me, such that my function is the best response in expected terms to your bid function.
We're thinking this from the point of view of the buyer, right? Who's trying to set up to maximize his utility.
Sure. Right, but we're looking at an equilibrium in the game in which you have two sellers competing, right? So they will need to somehow bid. The question is, given a cost realization, you know what your cost is, how much should you be bidding? This transformation beta 1.
Your cost, the seller, function from the seller's actual cost.
Yes.
To what he's going to bid.
Absolutely. And those two bid functions need to be in equilibrium to each other. In other words, one needs to be a best response to the other, and the other one needs to be a best response to the first.
But it's not iterated, is it? They make a single bid.
Yes.
And they don't know what each other's cost functions are.
Exactly. Well, they know the cost distribution. They don't know exactly the realization of the cost. I agree. Absolutely. Sealed bid. That's okay. Most of these contracts actually are allocated via sealed bids. There's one round of bidding and that's it.
So the beta 1 was on private to player 1?
Yes. And beta 2 is private to player 2. Okay? But they anticipate each other's bids in equilibrium.
So now tell us what phi.
Okay. So phi is, let me give you a picture. Phi is the allocation induced in equilibrium. That means what? Given the equilibrium functions, imagine, so this space consists of cost realizations for player 2 on the x-axis, cost realizations for player 1 on the y-axis. Okay? So whenever there's a pair of cost, or a vector of cost realizations which lie below phi, it means that the contract goes to player 1. Whenever there is a pair of cost realizations which lie above phi, the contract goes to player 2. Yes, if you want. Okay, so, but in allocation space, right, and this is an equilibrium result, right? I mean, we don't know exactly what beta 1 and beta 2 are. We cannot compute them explicitly, but we will be able to characterize these allocation curves. It's going to be the most important thing. And they have the following characteristics, which are very, very easy. So, phi of 0 equals 0, which means what? Which means that if both players are at their most efficient, they have the lowest possible cost which, in terms of their realization, then at this point, they will bid exactly A apart. If you're announcing this handicap A, then the bids for the most efficient types are going to be exactly A apart. And it's relatively easy to show from first order conditions that that's the case. Okay, so imagine the following thing. Imagine I would know what your bid is at 0. Right? If you're at your most efficient cost realization, imagine I would know what your bid is. Then clearly, I would never ever want to bid, if I'm the favored guy, A below you. Right? Same thing in the opposite direction. Imagine that you're the unpreferred guy and you know what my bid is at 0. Then you never ever ever want to bid A above me. These two inequalities tell you that at 0, the bids will be exactly A apart. A is public. As A, I've just announced, I've committed myself as an auctioneer to this rule. I'm going to handicap the auction by exactly A in favor of my preferred guy. Okay? So, no matter what A is, no matter what A I announce, and no matter what distributions I'm facing, we know that in equilibrium, at least this is true. At 0, at their most efficient cost realizations, the bid are going to be exactly A apart. Furthermore, there's another simple property. At 1 minus A, so imagine you're the unpreferred guy, and your cost realization is exactly 1 minus A, well, you have no shot in hell of ever winning this auction. Why? Because even a guy with cost 1, even an efficient, preferred guy who has the most inefficient cost can beat you at that point by simply bidding his cost. So whatever these phi functions look like in general, we can tie them down here and at the top. That's the most important geometrical part. Okay. Second price bonus auctions. Think of this as an open implementation rather than a sealed bid implementation, although it works either way. Here's how the rules work. I'm going to announce, in this case, a bonus, A. Bidder 1 and 2 draws cost independently as usual. Bidder 1 wins, in this case, if he has the lower bid. Okay. And bidder 2 wins if he has the lower bid. And bidder 1, as the winner, receives what in terms of compensation? Receives the bid of the other guy plus this bonus. I'm paying you a bonus of A just because you're my preferred guy. Bidder 2, on the other hand, my unpreferred guy, if he wins, just receives the other guy's bid as a compensation. Again, I'm going to restrict payoffs to be at most 1, so I'm not going to pay you more than your highest possible cost under any circumstance. But in this case, what's the advantage? We can find an equilibrium in dominant strategies. for this game, which says bidder 1, under these circumstances, should bid exactly his cost minus his bonus. Bidder 2 should bid exactly his cost. And from a game theoretic perspective, this is very important because these are dominant strategies. That means something very strong. These strategies do better against anything that my opponent could throw at me. So they do better than any other strategy I might pick, regardless of what my opponent is throwing at me. So they're very simple to understand, very simple to implement, and you don't have to have very big computations overall. Second point about these second prize bonus auctions, what do they implement? Getting back to our type space picture. Well, second prize bonus auctions will implement exactly straight lines, which are parallel to the main diagonal. Right? So these are going to be lines in which C1 minus A equals C2. So in the allocation space, the first prize implementation is some complicated shape. Second prize implementations are just going to be parallel shifts up and down from the diagonal, depending on what kind of bonus I'm picking. Finally, what is optimal in this universe? Or in other words, what would Roger Myerson do in this universe?
Quick question. Is that on that, if you just did the standard lowest bid wins,
Yep.
the full request proposals, then people just bid their costs. I mean, is that simple too?
So,
Or is that more complicated?
okay, if I'm doing just requests for proposals, then what's going to happen? I'm going to be implementing a line which is exactly delta above the diagonal. Right? In the second prize.
Similar than this SPBAS.
Right, then the second prize bonus auction. Right? The request for proposal. But the kind of standard auctions which you run, for example, I don't know, you bid, I bid, and the guy with the lowest bid gets picked, they implement what? They implement the diagonal. But in a first price implementation or in a second price implementation, they always will implement exactly the diagonal.
Okay, so they're all of them are simple.
Yep.
So it's only this handicap one.
Yep.
And what do you conclude from that? I mean, does that mean, are the simple ones good in some sense, or good because they're easy to analyze, or good because they're good under practice?
Okay, so let's be careful here. What do I mean by simple? If you refer to simple, what I'm proposing here with these simple handicapping and bonus rules, they're very simple to implement. You don't have legal restrictions on them. You can actually do them. And secondly, I'm going to show you that they come damn close to the optimal in general. Okay? If you mean by simple mechanism just standard auctions in which you bid, I bid, there's no bonuses, there's no handicaps, and the lowest guy wins, they will always implement the diagonal, and that's it. And they're going to be very, very poor in terms of performance.
That's the bit you haven't shown us
Yep.
yet.
I owe you one more slide before we can go to the full geometry. Sorry, I mean, expose in auction design. Okay, so now you can think of this as a kind of optimal mechanism design problem. Okay? Let me put it differently. What would Roger Myerson do in this universe? What's the optimal mechanism? So the optimal mechanism would give us an implementation, let's call it phi sub m, which has the following implicit equation definition on top. On the left-hand side, you have something called the virtual cost applied to phi m for player 1. On the right-hand side, you have the virtual cost of player 2, to which you're adding delta. Or let me put it this way. For a phi which satisfies this equation, that's the optimal implementation. That's the optimal allocation which you could get from an auction. So a couple of things you can show very easily, geometrically. First, that the optimal allocation lies strictly above the diagonal. Not a big surprise. I prefer player 1 to player 2, so the optimal allocation would want to give the contract to player 1 more often than to player 2. Secondly, if this f over f term, which is part of the virtual cost, is convex, then the slope of the optimal allocation is less than 1. If it's concave, the slope of the optimal allocation is greater than 1. So just from this, we can say a couple of things. The first price handicap auction doesn't look too smart. Okay? So let's put it this way. Phi m is going to be what Roger Myerson would want us to do, right? The optimal auction in this universe, the type of allocation which we want to implement. Well, we know that no matter what kind of bonus structure I pick, the first price auction is always going to start at this point in terms of its allocation. So we have too little distortion at the most efficient types. Right? So if I just happen tomorrow to run into two very, very efficient producers competing against each other, then the first price handicap rules are performing very poorly. Secondly, we have too much distortion at the top. Let's put it differently. I mean, I'm giving the contract to player one too many times when costs turn out to be inefficient. So remember how to interpret these pictures. Everything that lies above the blue line are all the cases in which I end up giving the contract to my preferred guy under a first price handicap auction. Everything what the optimum requires is to give the contract to player one whenever the cost realizations are below the red line.
And optimum, just to be clear, is minimizing the expected cost of the buyer.
No, optimum again means this combination of I'm getting the better product whenever it's worth getting it. Right? Given that, I don't know what the costs are. So it's combining the optimal level of price competition, which I need to foster, with getting the preferred good as many times as I would like to, okay, in expected terms. Okay, guys, so I'm done with the intuition. I mean, once we have this picture, it's pretty obvious what's going to happen. So, look, pick a handicap for a first price implementation. You get one of these blue lines. Okay? It will intersect the Myerson line, the red line, somewhere. Otherwise, it's completely suboptimal. So, but if it intersects somewhere, then I can do substantially better. I can just pick a second price implementation, like this green line over here, that goes exactly through that intersection, at least once. And if the slopes are correct, if I can prove to you that the slope of the blue line is everywhere greater than 1, and the slope of the red line is everywhere less than 1, then such a picture tells me that a second price implementation is always going to dominate a first price implementation in some very, very strong sense. For each realization of the cost I might have, you draw any costs out there, I cannot do worse with a second price implementation than a first price implementation. So even if I were to choose the optimal handicap in a first price universe, I could still do better with a simple second price implementation. And that's the key argument here. Sorry? With a bonus. Yep. Okay? So the clear advice here is the following, right? I mean, there's no reason in the universe why you should ever pick a first price implementation, right? A handicap of any form of fashion, when you can pick a simple open structure, or open auction, with a bonus that gives you always better results. And this is, by the way, not an expectation. That's the strength of the criterion. This is exposed. Right? Even if I were to know everything I know after the auction, I would still choose the second price over the first price one. So it's enormously strong. Good. So, go ahead.
So if the second price auction and the open auction are equivalent in theory, yeah, in practical terms, which one would you choose if you were voting? You that GE and Rolls-Royce, so
Well,
you make open bids, or would you say, okay guys, here are the envelopes, it's a one-shot?
Okay, so first, in theory, right, we have revenue equivalence, or these auction forms are equivalent only if symmetry pertains. If the costs are symmetric, then indeed first price auctions and second price auctions, and open auctions and so on and so forth are all equivalent, because they all yield exactly the same allocation, which is the diagonal. When asymmetry pertains, then that's no longer the case. Right? And kind of I mentioned the Maskin and Riley result earlier on, which said, by the way, if you were to pick just between a first price and a second price auction, no bonuses, no trills, no bells, then you should always pick the first price auction. What we're showing is in kind of a more realistic universe in which you can handicap the rules in favor of your preferred guy, because that's what it's all about at the end of the day, then with a second price or an open implementation, you will always do better than with a sealed bid first price implementation. And this always better is not in terms of just expected revenue or expected surplus, it's cost by cost. Right? For any realization out there which you could have, I'm better off doing an open implementation.
How hard is it to find this exact bonus in your technical curve?
But very good, and I don't know, by the way, what phi FP is, right? I'm never claiming anything about that. But my point is, all I have to do is look for the optimal second price bonus auction. And I know whatever the optimal second price bonus auction is, it's always going to dominate any first price implementation. And finding the optimal second price bonus auction, I'm going to show you in a second, is relatively easy. Okay, so what this picture says is, from now on, completely ignore first price implementations because they can't do any good for you. And it's kind of a very, very powerful result in that sense. I mean, I'm really trying to understate it here. In the paper, we're much more bombastic about how strong this is. If you don't have a preferred supplier, you can use anything you want. All of them are equivalent. That's the grand Myersonian result. If you do have a preferred supplier, then use a second price or an open implementation with a bonus, skewing the rules in his favor, rather than a first price implementation, any first price implementation. Okay? And remember, so the reason why we wrote this paper is because first price implementations are the norm rather than the exception in the business universe. Okay? People seem to be, for whatever reason, much more comfortable with them than anything else. And yeah, I mean, it's.
And when the preference is 0, it's equivalent.
Yeah, when the preference is 0, all these lines collapse to the diagonal. Okay, they're all the same.
So the reason that people typically use first price is just because it feels more intuitive somehow.
Correct. It feels more intuitive, but let me put it this way. I'm literally doing this for a living. I wouldn't know how to advise you to bid in a first price auction. Unless you would give me some very, very detailed information about the cost structure of your opponent, I would not know how to advise you to bid.
But as the buyer,
Mm-hmm.
if you don't have a preference,
Yep.
then your expected outcomes are equally equivalent, whether you use first price or second price.
Absolutely. As a buyer, if you don't have a preference. Yeah. But second point, let me mention. Let me get back to mentioning one other advantage. In a second price or open implementation, the bidding strategy is trivial. And we have a ton of experimental and behavioral evidence that people learn it very fast. It's based on dominant strategies. Dominant strategies are, let's put it this way, almost non-strategic. I have one strategy which does better than any other strategy at my disposal against anything my opponent could throw at me. This is no longer a complicated Nash equilibrium computation in which I have to best respond and so on and so forth. This is kind of, hey, this is the best strategy, period. And that's very easy to learn and very easy to implement. It just says, okay, bid your cost if you're the non-preferred guy, and bid your cost minus your bonus if you're the preferred guy. End of story. We can all go home. And people actually learn this, and we have evidence that people understand this very quickly. You play 3 rounds of a second price auction, you're going to figure out what the equilibrium strategy is very easily. While first price implementation, God knows, we can't even compute the equilibrium functions that go behind the blue line. Okay, I don't know what they are. I know that they exist.
For the buyer, he doesn't really care. Right? But you're saying for the good of mankind, why waste
No, it's not for the good of mankind, because you can make errors. Okay, if you're uncertain about what kind of strategy to pursue, you tend to become much less aggressive in your bidding. And especially if you have a little bit of risk aversion out there, then you become extremely. So it's not for the good of mankind; it's for the good of the seller. Yeah. So I mean, we're predicting here equilibria in under risk neutrality and so on, but add just a little bit of risk aversion, the whole thing goes out the window. And if there's an additional layer of ambiguity in the bidding, again, tons of experimental evidence that people go all over the place. Exactly.
The second price option, I don't need that. This is a result.
Mm-hmm.
That depends on this assumption, right?
No, that's a general result in auction theory, right? So for first price auctions, even if it's a symmetric universe, your bid is going to be highly dependent on your beliefs about the cost distribution of the other guy.
No, I mean here you have assumed f over small f is common.
Oh, okay. The assumption here is tied to what? I just want to show that, look, this picture works if the blue line has slope greater than 1 everywhere, and the red line has slope less than 1. This f over f convex assumption is exactly that the slope of the optimal implementation has slope less than 1 everywhere.
So if it's not the case, you cannot ensure that second price.
I cannot ensure the optimality everywhere, but I'm going to show you something else. Sorry, go ahead. Sorry, I didn't hear the beginning of it. Mm-hmm. Yes. So that's okay. So 60 pages of math later, I can actually also show you that how it works with multiple player. Yeah. Although the two-player result is also it's actually the key to everything, because at the end of the day, the competition is going to boil down to a two-player competition. But if you get that case solved, the rest is okay. A couple of layers of mathematics later on, but that's it. Okay, so that being the intuition, we rule out one important thing. I mean, we rule out, sort of the interest in first price auctions. So in order to make this a theorem, so 60 pages of math is to ensure these two conditions, that the slope of the allocation of the allocation function implementing the first price auction is greater than 1 everywhere, and the slope of the optimal allocation is less than 1 everywhere. How do we prove it? Well, here's an idea of the proof. How do we prove this crucial part about phi prime greater than 1? Well, we know something about phi prime at 0. We know something about phi prime at 1 minus a. So therefore, if it's ever below 1, it must have a minimum which is below 1. So we can use the first order approach to it and try and rule that out. But again, it is quite a messy procedure. Good. So assumptions in the symmetric case. What do I mean by symmetric case? If the two players actually happen to have exactly the same cost distribution, then if convex virtual costs prevail, assumption 1 is about slope of the Myerson line being less than 1, delta greater than 0, and assumption C is a regularity assumption on the distributions which I need to prove my key result. Under these three assumptions, never, ever, ever use first price auctions. Let me just say that these assumptions are not very demanding from an econ perspective. I mean, they're kind of the standard regularity assumptions which you're going to see over and over and over again in mechanism design, but I'm happy to discuss them later on. Now, note, how does this compare to Maskin and Riley? Remember, Maskin and Riley said that, all right, if you would have these preference asymmetries, then a standard first price auction, no bonuses, no thrills, no nothing, is better than a standard second price auction. Well, yeah, perfectly cool. What we're showing is that any first price auction is dominated by some second price auction with a bonus out there. There is an optimal bonus which implements something which is substantially closer to the optimum than what you could ever implement via first price rules. So it's only an apparent contradiction. It's, we're generalizing, if you want, their result. Okay. Is the result robust? Yes. The result is robust in the following sense. Imagine that the distributions now, the cost distributions themselves are no longer symmetric, but they're actually asymmetric. And on top of that, I have an asymmetry given by my preference parameter. Does my result still hold? Yes. And here's a whole long list of assumptions and a theory in which I'm not going to go into. Just to mention the following thing. What this result shows is the way in which we constructed the asymmetry shows that, for example, proportional bonuses or proportional preferences don't change the nature of our results. I mean, I think you asked about it earlier. What if my product is better than Peter's product by 10% or by 50%? So whether you're moving about, whether you're talking about a fixed preference parameter or a proportional preference parameter, nothing changes. Okay? So the results are robust to that. Secondly, now this is something slightly stronger and gets back to your question. If I can actually assume that the density is increasing, so the distribution function is convex, then the result carries true for n bidders in any kind of combination of forces. And finally, implementation, because that's the interesting part. So for implementation, what we asked ourselves is the following question. Look, suppose now you're indeed the seller, but you really don't know yourself where these cost distributions are coming from, which is a reasonable assumption, right? I mean, maybe I have uncertainty about what kind of cost distribution I'm actually facing. Precisely. But I mean, now imagine that you're the seller on top of it. So you're the seller, okay. And you, furthermore, you don't know anything about the cost distributions. So I can just announce the second price auction? Exactly. But the question is, how big a bonus should you announce? Oh, well, that depends on your preference. Well, that depends on your preference, but I mean, how is it going to depend on your preference? All right? So, I mean, you know, am I going to announce, as you suggested, like, you know, the full bonus? Right? I could, if I prefer by 50,000, should I announce 50,000? Should I announce something less? Answer, in general, you should announce something less, and strictly less. Okay? But more important than that is to give some sort of rough guidelines. I mean, what you're going to announce is obviously going to depend on your delta, on your true preference. But also it's going to depend on the distribution, which you believe to be true. Right? But if you don't have a good idea about the distribution, then what should you do? If you want to think of this as kind of like a question of reserve prices. Okay? What kind of reserve price should I announce if I don't know what kind of distribution to expect? Okay, so here's our measure of optimality. Now we're going to think only about, you know, what's the best second price bonus auction? What's the best bonus I can announce, and how well can I do? And we picked on purpose a horrendously hard measure in terms of implementation. We're going to ask ourselves, how much better does our second price bonus auction do relative to the symmetric universe versus how much better the optimal auction does relative to the symmetric price auction. Right? Anybody can run a symmetric auction. We're going to try and actually maximize this ratio over here. And optimal is Myerson, right? It's impossible to implement most of the cases unless you have very, very precise information about the distribution. You need to know the virtual costs by themselves. Okay, so if you know the distribution, I can find you, classes of distributions, pretty large classes of distribution, in which this ratio is 1, meaning that our second price bonus auction actually implements the optimal, actually implements us what Myerson would want. But that's not really the question here. The question is, what should you do when you don't know F? And we have a whole bunch of results. But let me show you, and they're all going to depend on this. What do you know about the slope of the virtual costs? Now, this seems like a very, very complicated problem, but it actually turns out to be very simple. There's natural correspondence between this and anything you might know about the density of the distribution function. All of these are economically relevant terms. So let me give you a flavor of results. Okay. So earlier on you asked me, like, what happens if the slope of the Myerson line is greater than 1 rather than less than 1? So imagine that virtual costs are concave. That would be the case in which the Myerson slope is greater than 1. In that case, just by picking a bonus, which is 2/3 of your actual value, you can guarantee yourself a rate of, what is it, 89%. Right, so you're getting 89% of whatever Myerson could get on top of the symmetric auction. You're getting at least that back via our second price auction design, which is the flavor of results. And there's many examples like this in the paper. Note, all I'm saying here is you don't need to know the actual form of the distribution. I don't need to know that it's a beta or a gamma or an exponential or a uniform or whatever it is. I just need to know, for example, that it produces concave virtual costs for this result. Then picking a bonus of 2/3 delta, your preference, guarantees you at least 89% of the gains which Myerson would guarantee you. And for different assumptions about distributions, we get different bounds. So we get, my co-author is very, very, very proud of our 48/49 result. Okay? If you know something about virtual costs, you get essentially 95% of what Myerson would give you. Good. This particular result is for symmetric distributions. So everybody draws their cost from the same distribution, but irrespective of the number of sellers. No. So the costs can be symmetric, but you still have a preference of one guy over another. That's equivalent to an asymmetric cost. Yep. Okay. So if there are no asymmetries in the cost and you only have a preference over one guy. All right. Obviously, the bonds get weaker the more asymmetry you throw into the problem. So again, there's like maybe 6 or 7 results like this in the paper. I'm not going to go through each and every one because I'm out of time actually. So robust techniques for thinking about asymmetric first price auctions. Again, these are mechanism free. There's a whole bunch of implementation advice, and I'm perfectly happy to talk about other applications and so on and so forth, but I think I'm out of time. Mm-hmm.
So as they are competing for our time, don't they learn about the cost functions a little bit more?
Sure.
I'm trying to figure out here how much of this could be observational versus analytical. This is a very broad question.
No, that's fair. Look, I mean, so let me put it this way. If you know what the distribution of the cost of your opponent is, perfectly fine, right? I can actually write the first order conditions and actually tell you, what you should be bidding. But again, that's not a dominant strategy equilibrium. It's a standard, Bayes-Nash equilibrium, meaning that in expectation, your bid is the best you can do given your opponent's strategy. Which means that if your opponent screws up, you might be well off as well. Okay, so it's again a very, very complicated, implementation. Secondly, if you as a seller actually observe the cost distribution, then it is relatively, we have the techniques in the paper, it's relatively easy to compute what the optimal bonus should be. Okay, I can actually tell you what is the optimal implementation. And for various distributions, the optimal second price implementation is actually the Myerson line. So you actually get full efficiency. Well, you would never get full efficiency on their first price.
You mentioned the example of a lot of engines and electric engines. Can you
that a sort of
Oh,
similar example, a Berg example, or is it sort of different?
no, fair. I mean, in terms of sellers knowing each other's cost, right? I mean, repetition helps. Repetition also fosters collusion, which is again problematic, right? And collusion is much easier in first price formats than in second price formats. Second price formats have the additional advantage that they're collusion proof. But how do people actually bid in these universes? I mean, literally rules of thumb. Okay, I mean, I've heard some of my students, who work for procurement for relatively big firms, they bid cost plus 20%. That's their bid. If it's accepted, great. If it's not accepted, again, great. So what actually happens, behaviorally, can vary from extremely, risk-averse situations in which people, bid extremely mildly just to make sure that they not get punished under any circumstance, to some heuristics which are cost plus 20. Okay.
A non-technical question. How would such results find their way into practice? How does this work? Do economists pick this up and then they advise companies that they
Right. I mean, we advised, for example, Boeing to drop. They had only, basically, their entire procurement was run by first price auctions with handicaps. They had a scoring system in which, I don't know, if you were a supplier which had worked 3 times with them and had proven your reliability, you were getting some points corresponding to bonuses. Okay? And then we advised them to completely drop it. Right? I mean, to continue having a point system, but to use that points as bonuses rather than handicaps in the auction, and use an open implementation. And I mean, how much headway we are making, I don't know. my students are MBAs, so I'm hoping, like, one generation down the line, people are not going to run first price handicap auctions anymore. But it's hard to persuade people based on, how should I put it, a 60-page dense math paper. So we actually looked at organizing experiments based on that. It's still forthcoming. So we'll see what the experimental advice suggests. Differently, guys who organize procurement auctions, so there's a whole bunch of sites which to which you can outsource your procurement process as a company, have been using kind of open implementations with bonuses like this for a long, long time. Okay, so there is, how should I put it? Our examples are not completely isolated. I mean, we're not, I don't know, preaching in the desert. There are some people who have figured this out on practical grounds from a very long time. But let me put it this way. This is relatively hard mathematical. I mean, for us as economists. I mean, the standard was the Maskin and Riley result, which said, like, well, by the way, I mean, kind of intuition, first price under asymmetric universes, yeah, they're actually usually better than second price. So people took that kind of, it was one lemma in one paper, very well hidden under lots of assumptions, and people took that advice kind of and went to the market. Like, yeah, okay, we can do that.
That gives some hope for you.
Yes, well, we hope so, right? But unless I get the Nobel Prize pretty soon, my co-author has given up on getting the Nobel Prize, so we're not going to compete with Maskin anytime. So,
yeah, thanks so much. We ought to finish with round of schedule. So, thanks very much.
thank you.